everybody. Good afternoon. Welcome to the webinar. This is the second of our learning series. The target of this webinar is to talk about granulation and drying monitoring. Before we start the presentation, I have a service communication because last week some people had connection problem. So the webinar ID is the one that you can find here on top of the slide. If you are able to connect with your computer audio, you are fine. Otherwise, there is a bunch of local number that you can call in, and just typing in the webinar ID, you can listen the audio in a proper way. This is the agenda for the event, for the learning series. Last week we talked about pharmaceutical identification. Today is the day for granulation and drying. Next week we will discuss about blending and monitoring. Afterward we touch base on tablet compression and coating. And last but not least, May the 13th, we will introduce the PAT UX and WUX that are the hazard location product. For today, this is the agenda. We will have a welcome and a company profile. I'm sorry for the people that were online last week, but we had more than 100 registered attended for the last week. This week we are basically double in terms of number, so I think that it's good to repeat at least quickly the company profile and the linear variable filter technology. Afterward, we'll jump into the application side, discussing regarding application on the NIR in an high-shear mixer, application on a fluid bed dryer, or in a fluid bed granulator. Afterward, Christina will show you an example and with a live session. At the end, there is a section Q&A. I kindly ask you to, because we saw that last week it worked pretty well, we kindly ask you to type the question in the question table in GoToWebinar. We will try to select the most interesting question, and we promise you to reply in a written form by tomorrow. All the questions. I introduce myself. I'm Emiliano Genorini, account manager for the EMEA and for the Latin American area for the MicroNIR product, and also Christina Malegori, that she's our field application specialist.
Hi everyone, also from my side. We will speak later.
Couple of words regarding the company. Viavi Solution is an American company. We are two big business units. One is called NCE, Network and Service Enablement, and the other one is OSP, Optical Security and Performance Product. The MicroNIR product line is inside the Optical Security Performance Product, and this is business OSP business unit timeline. So the company started the activity in 1948 with the name of Oakley. In 2000 it became JDSU, and in 2015 the name changed again to Viavi. Where the OSP business unit of Viavi is working? In a spectral sensing, where the MicroNIR is inside, but we have also a lot of activity in the consumer electronic, mobile phone and computer, for example, government and aerospace, anti-counterfeiting product. The pigment for the banknote is a very important product for us, and also in the automotive market. So as you can see, we have a very wide range of application inside our. The headquarters of the OSP group is in Santa Rosa in California, where we have operation, R&D, and sales and marketing team. What is the MicroNIR vision? This is a very nice slide that I really like, because it's explaining basically from a traditional mechanical watch to one of the latest smartwatch in the market, the evolution that happened in the watches, but is the same in a lot of other electronic products. We can think to the mobile phone, or even from the floppy disk computer, from the desktop floppy disk computer to the latest computer with the SSID. What is the philosophy of the vision of the MicroNIR? Enabling a smarted world. Enabling a smarted world working on 4 cardinal points. The miniaturization. The MicroNIR, especially the 1700 ES, is a very small device. The device is 64 grams, if I'm not wrong, less than 4 centimeters tall, and is very miniaturized thanks to the linear variable filter. In the other side, we have, in the opposite side, the performance, because the MicroNIR is a system that is somehow designed to be a professional tool. So we have some performance like the signal to noise that is around more than 20,000 to 1. In the two sides, you have the affordability and the connectivity. Affordability means a good, reasonable price for a application that is fit for the purpose. Connectivity, we can read connectivity in 2 different ways. One way is when you have an handheld device, maybe not in the pharma, but in all the other markets, it's very important to have a cloud infrastructure. So connectivity through the cloud, enabled using a Bluetooth communication in the on-site product line, but also connectivity with HMI or the pharmaceutical equipment using something else like the OPC, UA, and DA. As you see, we have handheld device and process products. What is the technology that is inside? Is the so-called linear variable filter that is one-dimensional, continuously vary bandpass filter. The filter is fabricated on a glass using hard, dense, and stable inorganic material for a long life and for a big environmental stability. This is allow us to make a very small device with some features that we'll see in a while are very important. The Viavi linear variable filter has been developed for the NASA, as you can see. So it's something that by design has to be extremely compact, lightweight, and robust. This is the layout of the MicroNIR. You see that you have 2 lamps here that are emitting the light that is going to the sample, and afterward the light is coming back, it goes into the light pipe. There is the linear variable filter and the InGaAs detector in a very small space. It ends up that the device is very small, and this is an advantage for some kind of application, but there are no moving parts. And the fact that there are no moving parts is for us a key point, because it means that there is no risk of misalignment, there is a long-term stability and 100% transferability between the different units. On top of this, we need to consider that there is no fiber optic. There are no fiber optics inside. So nothing that can be damaged or wear out. There are no replacement costs and is completely insensible to the temperature variation. Quickly, regarding the product line, as I promised, we have different instruments. We will see in the next slide, but all the instruments are available in the OEM configuration, so with the SDK, or with the full software suite that is our MicroNIR Pro software that is 21st CFR Part 11 compliance, and we have the USP 1119 and EP 2240 validation procedure embedded. We also developed a lot of accessory for our end user product, for example, different kind of flanges or extended probe to go inside a fluid bed dryer or specific probe to analyze tablets. This is the MicroNIR 1700 ES, that is the, let's call it original MicroNIR, and the device is connected with a cable, with a USB, and you can get the measurement. Here you have, three of, the most important product that we have. We have the on-site W, that is a Bluetooth device, that is an handheld device with a lithium battery inside that can work up to 10 hours and is IP65 and 67 rated to be used in wet and dusty environment. In the other side, you have the PAT-U and the W that are two process systems by design for, in this case, IP65 and 67 rated, that are normally used for pharmaceutical application. In pharmaceutical application, in a lot of cases, we need to use the PAT-UX and the WX that are similar to the U and to the W, but on top there is a certification for hazard lock environment. The UX is 2.1, just to summarize, even if you read the label is more complicated, and the WX is 2.2. This is a thing that it's really important. Let's start to talk about the application, process analytical technology. This is a slide that I really like because we have on the left-hand side the raw material, and normally we try to keep the raw material as more constant as more as possible. But unfortunately, the raw material are somehow variable by nature. It's impossible, even if we buy the same kind of product with the same code, with the same whatever we want from the same supplier, there is anyway a small variation. If we keep the process constant, it's crystal clear that at the end the product will be variable. So one of the things that the process analytical technology that is important for the implementation of the NIR, the NIR is one of the most classical implementation, is to understand the process in order to understand as better as possible the critical attributes that are operating in our process, and somehow find a way to define a sort of sweet spot where our process is immune, is able to digest the variability of the raw material in order to get a constant output. Where the NIR can be applied: raw material, blending uniformity, granulation, loss on dry, compacting, and tablet. Everything can be connected from the hardware side, from the mechanical point of view, but also can be connected from the computer side with OPC, UA, and DA. This is quite interesting stuff that is talking about about the cost of quality. With the traditional quality by test approach, it's on the left-hand side. It's very easy and fast to introduce a new product. But once you come across something wrong in the production, that bring you to an auto specification, you need to invest time to, let's say, understand your process, and it come up that the development effort, it goes up. Using an NIR sensor, especially in the developer phase, using a quality by design approach, you have for sure in the beginning a sort of learning period, but afterward the process is under control, and it's very unlikely that you have an auto specification. And in case you have an auto specification, you know the point that you have to touch to make a contingency plan and make a corrective action. So let's move one step more in the process. For granulation and drying, we can barely simplify the option available in 3 different. One is a multi-step approach where we do granulation in a high-shear granulator and we dry out the wet mass in the fluid bed dryer. Or there are 2 other options where we do everything in a single pot, let me say. One is the high-shear granulator where we dry inside the high-shear, or a fluid bed dryer where we do drying and granulation and drying at the same time. It's interesting to know that we can have 2 options to monitor this kind of project. First of all, we can do measurement online using physical parameter like the impeller torque, or the temperature of the air, or the humidity of the air. But as you can see, are real-time measurements, correct? But so there are no sampling required, but are physical measurements. There are not direct measurement of our chemical entity. If we want to measure the chemical entity, we need to take a sample, make a Car-Fisher or a loss on dry with a thermobalance, or eventually we can measure the particle size with a particle size analyzer. But in this case, we have removed a sample from the process, so sampling is required. We go to the laboratory, and there is a long time to get an analysis compared to the process. Let's assume that the drying process is 20 minutes globally. To do a Car-Fisher when the moisture is like 10%, it probably take 5 minutes, mean that even if you are super organized, you can do maximum 4 samples, ignoring completely what is going on, let's say, in the between. So it's clear that the possibility to apply an NIR sensor to such a kind of process is a plus, because the NIR is able to acquire spectra in a very short time. Very short time, I mean few seconds, 1 second, even less in some cases. This is an installation that has been done on an high-shear mixer. The high-shear mixer is designed to also granulate and also drying the product. In this case, we are just granulating, but anyway, there is a heating jacket. So technically speaking, we had to, let's say, insert a path U, that is this one here, and as you can see, there is a windows that avoid the direct contact of the MicroNIR with the internal chamber of the granulator. Here you have a couple of pictures of the and this is a quick video that is explaining how has been done the installation. In this case, we decided to use, in the case of the video, the extended probe and not the so-called welded flange, but the installation is pretty similar. This is the experiment that the case study that I want to show you. So lactose monohydrate, PVP and PVP echolidon as a granulator agent. And here you have the spectra that we acquired every second. You see from the color that there is a clear sequence in our spectra. And if I do the data pretreatment, applying a first derivative plus an SND, I get this picture. This picture is a picture that in the beginning surprised me pretty a lot, but was confirmed doing several experiments on the same, replicating the same experiment. And the thing that surprised me is that if you look at in the beginning, this is the 1428 is the water peak. You see that it's not a surprise that the water content is increasing because we are adding the binding agent that is somehow based on water. But the thing that is quite interesting is to see that there is a sort of shoulder here, a little bit on the left-hand side, that is growing up as more as we go ahead with the granulation. And the physical explanation is the one that is here below. So there is a transition between liquid bridge, solid bridge, until we are creating the so-called snowball structure. This is an important point to consider because is normally not so easy to see the transition between liquid, solid, and snowball. And I want to show you this one that is another interesting plot where we picture out the moving block standard deviation in red, the moving block mean in green, and the impeller torque in blue. You see that there are clearly three phases: the dry mixing, the wetting, and the massing. Okay. You see that in the dry mixing, the standard deviation of our spectra is changing, meaning that our products are mixing each other. And I mean, it takes roughly 90 seconds, 95 seconds to be. You see that this phase is not absolutely visible using the impeller torque. But going ahead, when the transition between wetting and massing is happening, we have a flex of the blue curve. Look at how clear is the variation using the moving block standard deviation. So what is the plus of using an NIR here? First of all, that you can monitor the dry mix, and you can be sure that your powders are mixed properly before starting the granulation. Thing that you don't have using just the impeller torque. The other point is that you can clearly see in a very clear way the transition between wetting and massing in a way that is for sure something that is not so obvious using the impeller torque. Fewer is the better, Christina is just to say. So if we don't need to use the principal component analysis, it's maybe redundant. But what the principal component analysis are showing here are showing, if you look at the loading, that the principal component 1 is this peak here. The principal component 2 is has somehow wavelengths that are important a little bit in the right-hand side. And this is confirming exactly this one, the slide number 1 with the number 2 of a spectra. So one is this peak, the other one is the other one here. So the principal component analysis is able to split between the two kind of water peak with different intermolecular infrastructure. Let's now try to have a look of the application of the MicroNIR to a fluid bed dryer. One option is to work through the windows like this. Another option is to work with an extended probe. Go quickly here because there is a video that it allows me to show a little bit better the installation. So this is the MicroNIR installed. We connect the cable, and inside you will see the flange. As you can see, the MicroNIR is never in contact directly with the product, and this is important for cleaning in place and sterilization in place, because there is just a windows that can be cleaned as you like, and so the instrument is never really in contact with the material. This is the extended probe that is attached with a sort of screw. And this is how is connected the extended probe into a fluid bed dryer. In this case, you will see there is the shaft of a device that is in direct contact with the material. This is a good point. When we should work through the windows and when we should work through an extended probe, using an extended probe. It's very hard to give a general statement. Normally, when I can, I prefer to work through the windows, because working through the windows, it allows me to avoid a process perturbation. As I said, I can clean the product, the windows as I like, and I mean, it's very scalable and easy to use. The extended probe is suggested when you have a very sticky material, because like this you can put the probe more inside, so the fact that there is a pooling or a cross on the probe is less probable than using a welded flange. And eventually going inside, you can part with air, have a scraper or a spoon. Obviously, it's a little bit more perturbative because you are putting something inside the fluid bed dryer. This is an example where we made basically we took the wet mass that we got from the previous phase, from the high-shear mixer, and we dried out here. You see original spectra and pretreated spectra. There is no, compared to the previous one, the water peak in a first derivative, it keep its own symmetry, and this is quite interesting to see. And here we put together the moving block standard deviation. Look at the brown line, this one. And we compared the NIR measurement with the classical physical measurement that are normally available on the fluid bed dryer, like the air temperature, the humidity, and the product temperature. You see how clear is the endpoint of a drying process with the NIR, definitely better than the other normal measurements. It's important also to consider that we are measuring a chemical entity and not a physical parameter that is changing upon something else that happened. So here is a direct measurement of a water content somehow. This is a real example that was one of our first application, and it is interesting to see because we made 3 batches, 1, 2, and 3. It is a high-shear mixer plus a fluid bed dryer. Here we are referring only to the drying phase, and classical PVP and lactose. and the humidity in the beginning was around 20%, and it ended up with 1.5% for all the batches. Looking at the spectra shapes, frankly speaking, it's almost impossible to see variation between the three batches. And also, the beginning was 20%, and at the end, the moisture was 1.5%. So using a traditional approach, not with the NIR, the three batches are the same. But when we made the moving block standard deviation analysis, we saw that the batch number 1 and the batch number 3 are behaving in the same way. The batch number 2, no. So we immediately started to doubt regarding the algorithm, no? But we try to calculate, as Christina will show you in the live section, a principal component analysis. And the funny stuff is that, again, the batch 1 and the batch 3, they have a similar trajectory. The batch 2, it behaves in another way. So it's really something that is inside our sample. We don't know, looking this graph here, what it is, but I think that we could state is that there is something that is unexpected in the batch number 2. So the NIR should raise a red flag saying, oh, look at this, there is a problem, you need to investigate. And actually, we started the investigation with the customer, and he came up that the batch number 1 was done at 9 AM, the batch number 2 was done at 12, and the batch number 3 was done at 3 PM. The batch, again, these plots are referring to the drying process. It ended up that because it was very close to lunch time, they decided to make the granulation in the high-shear mixer few minutes shorter, because the product, looking by eyes, was somehow good, and it ended up that probably the particle size was different. And with the different particle size, when you dry it, you maybe arrive to the same concentration, but with you keep the particle size at a different, let's say, value. And also, if for sure you go there going around and not with the same direction of the other two. So it's important, this one, because it's not important that the moisture is 1.5%, but the NIR here is giving the information that yes, the moisture is 1.5%, but also that you reach at that point using the wrong way. So maybe there is something different in the particle size that can impact your product later on, for example, when you do the compression. Last but not least, this is an example of granulation and drying, where I try to avoid for all my presentation to make a PLS model. In this case, I want to show you a PLS model for the loss on dry and the PLS model for the D50, so for the particle size. I was kidding, say that I was trying to avoid as much as possible the PLS, because as long as I do a explorative analysis, a trend analysis using the moving block or using the PCA, I can be very flexible in an R&D lab, because I don't need to create a model before having data, but I can get the data from the batch number 1 and start to have important information without building and investing time to create a model. But the message that I want to drop you is that with the MicroNIR, you can also build a quantitative model. To build a quantitative model means that the NIR is reading in continuously the product inside the fluid bed dryer. At a certain time, you take out a portion of the sample, you note the time to associate it to the proper spectrum, you take the sample, you do the loss on dry, you do the particle size analysis, and afterward you make the correlation. The result is this one. This is a prediction that you can have directly online with the NIR, and this is a comparison between the predicted loss on dry NIR and the real loss on dry calculated with, I think, a thermal balance in this case. And this is the same for the D50, that is the central value that you can get from a particle size, but the same can be done for the D10 and the D9. The advantage is that you don't need to take out a sample, you don't need to go to the laboratory, but everything can be completely automatized continuously with the NIR. This is the end of my talk. I want to give the stage back to Christina, that she will show how the MicroNIR work in a real life, so the MicroNIR in action.
Yes, thank you, Emiliano. I'm now sharing my screen. Can you confirm that you can see my screen?
Yeah.
Okay, great. So for the one of you that had not the possibility to attend the webinar last week, my name is Cristina Malegori and I work in Viavi as MicroNIR field application specialist. And I can do this work thanks to a collaboration with a university, that is the University of Genova in Italy, in which I have a postdoc fellowship in the group of analytical chemistry and chemometrics. And in Viavi, I'm also working for the educational program. And these learning webinars are part of this program that includes also schools and a dedicated webinar for the software. My research activity is focused, of course, on NIR, but in particular on multivariate data analysis. So the aim is to extract the information that we are acquiring with the spectra, try to understand what is happening in our process or in our product. But today, we will focus on a specific case study. I have with me a computer and a PATU device, that is the one that can be directly implemented in the process that we saw in the videos that Emiliano just showed us. And I will work with the MicroNIR Pro software. The version is the 3.1. And we will focus on something advanced like the live mode acquisition that we will see together afterwards. And what is the case study? So as you know, I'm at home, so I have to create something that I can do with simple tools and with simple stuff that I can buy in the supermarket. So I have some distilled water and some ethanol, and I create a solution that has 2 parts of ethanol and 1 part of water. I already acquired lots of batches to have the golden batch of the drying process. So our idea is that I want to follow the drying process just using the NIR to see what happened to this solution when it is exposed to air. So what we will do is to model together the data that I have already acquired this morning and then prepare the solution together. So I will prepare the solution for you, put some drops of the solution on a tissue and then acquiring directly the dehydration phase thanks to our PATU device. As we saw from the presentation of Emiliano, we can follow this process mainly with 2 approaches. One is called moving block and is a simple approach that we will see next week for blending purposes. But today we will focus on PCA, principal component analysis, and in particular on principal component analysis projection. Why we decided to focus on these? Because principal component analysis is able also to understand the process, not just to monitoring it. And so we will see together this process interpretation. But what is principal component analysis? So I used to call this approach the queen of chemometrics because it's one of the most common and most applied algorithm, not only in chemistry, but also in econometrics and in many other fields. And this is just a decomposition, a construction of new uncorrelated variables, starting from all the variables that we are acquiring along the spectra. So we start with more than 100 spectra, and we will resume the whole information in 2 or more than 2, but usually 2 new variables that are completely uncorrelated and orthogonal that are called principal component. But the advantage of this technique is that we obtain 2 really simple and straightforward graphics that are the score plot that allow us to evaluate the similarities or the differences or the trends along the samples, and the loadings. The loadings are the reason why we can underline these similarities or differences. So is a focus on variables, while scores is a focus on samples. In more detail, PCA has a really useful procedure that is called PCA projection that allows us to overlap the spectra and the PCA of different processes, one on top of the other, allowing to mainly follow the process and see how the process is behaving in respect to other spectra that we acquired before. But I think that we have done with the slides, and we will move to the software. So as I told you, first of all, I want to look together to the data that I have acquired this morning. So this is the environment of the MicroNIR Pro software. And first of all, we will focus on the data analysis package, and in particular on principal component analysis, PCA. I click here, I create my new model that I will call PCA drying. And now I recall a calibration set of data. So I'm recalling the golden batch that I want to model that I already acquired this morning. So I have here my cal dry, that is my calibration of the drying process. And here I have the all the 38, if I remember properly, yes, 38 spectra that I have acquired this morning. So first of all, what I want to do is to add some spectra pretreatment. So SNV and first derivative are the simpler one and really useful one, but we don't have time to enter in detail here. And then I want to generate my principal component model. Here is asking me how much component do you want to model? Not interesting right now, just say 5. Wow, great. Here we have 4 different representations. Let's focus on these 2 that are the ones that are interesting us for drying, for following the drying process. And here we have a really evident profile made by simple dots. So these dots are the samples. So it means that if I color these points, I said 37 or 38, I don't remember, 38. Okay, here I have the different colors that can show me that here I started the drying and he's proceeding until this point that is change direction. So I have something that is changing along the x-axis, that is called principal component 1, and something that is changing along principal component 2. And if I want to chemically understand what is happening here, I can look at the loadings and ask for looking at principal component 1 and 2. And I can see that I have different spectral signature in the loading according to different direction in the scores. It means that I was able to deconvolve the contribution of alcohol and water inside the solution that I was monitoring. So this is the advantage of PCA, not only following the process, like in the moving block approaches that we will see next week, but also process understanding. So if I'm happy with this model with the golden badge, now I want to see if the new spectra that we will acquire together are similar to this pattern or not. So if my process is consistent, if it's doing every time the same job. So I want to save it, PCA drawing, okay. And I want to move to the live mode. What is the live mode? It means that I will acquire the spectra together with you and they are directly projected into the PCA scores. So I choose my PCA drawing, that is the model that we want to look together, and just 2 components that are enough for explaining our process. Okay, now the software changed the interface. This is the interface for acquisition. So I'm ready for scan. I already put the name of the sample and all the other stuff, but I want to do together the dark reference that is done with anything in front of the sensor, and the reference scan that is done with the spectralon, that is a material that reflects 100% of the light. And now I take a paper, tissue made by paper, and 2 drops of liquid, 1, 2. I take my device, I put it on the paper, I fix it, and I can just say sample scan. And here we will follow together the acquisition during the drying process. So you can see that the spectra are moving down, down, and even lower. What we are doing here, we are acquiring according to this configuration. We are acquiring in reflectance because I'm acquiring a tissue, so it's not a liquid, it's just a drop of liquid on top of the tissue. I'm doing 100 scan, so each of these spectra is the results of 100 spectra that were acquired before giving me the results. And I'm using the automatic scan mode with the continuous scan mode. It means that I'm not clicking the software for acquiring the spectra, but they are acquiring continuously and autonomously. And I decided to set 1 spectrum for every 2 seconds for a period of 2 minutes. This is just for the trial, but you can choose also to acquire spectra, I don't know, every hour for 9-10 hours, as you wish. There's also another interesting function that is the lamp of dark scan that is able to balance the effect of temperature, because if I have a really long process, temperature can change. So I have just to click here and every scan is automatically correct thanks to the acquisition of the dark background for every spectra acquisition. Okay, so we are more or less at the end of our 2 minutes, and you will see that the scan will stop automatically, okay? Then I can remove the sample from my device, and we can see the results on the PCA. So we can see that without doing anything, I have these dots plotted inside the orthogonal space of the previous principal component. But if we want to take a look and a more in-depth focus on principal component, I can upload again the model that we perform on the golden batch and add here a validation set, just to see if I can validate the profile that I have obtained the first time. So I retrieve my data and I take the data that we just acquired together, retrieve. Here I have my sample. I have just to tell to the software that I want to use the validation set, and I regenerate my model. So now I have PCA drying 1, that is the regenerated model, and I can plot on top the second batch that we just performed. And you can see that we have a complete overlap of the first batch, the golden one, the one that I want to consider as reference, and the one that we just acquired together. So it means that principal component analysis can be used for understanding the process, for following the process, and also to detect problem of the process. So if you see the PCA projection that is going out of the golden one, it means that something is going wrong inside your system, inside your process. With principal component analysis, I have finished. Of course, we have lots of other interesting functionalities in the software, but my time is finished. So I pass the stage to you and to the question time.
Thank you, Cristina. I think that there is some interesting question that, as I said, I want to reply immediately. Some other question that we will reply by mail. One of the most, let's say, most important question is what is a moving block method? Can you take it and just spend a few words on that? I know that is the topic for the next week demonstration, but maybe you can just give an idea.
Yes, of course. So what is moving block? In moving block, we are just, if you want, maybe I can also perform it right now.
Up to you. I think that maybe just
yes.
the
What we are doing here, I'm just adding the same spectra that we saw together, the one of the drying, and I can just calculate the standard deviation of this spectra. Is something that I didn't try before, but we can do together.
I make you the presenter again. Apologies.
Yes.
I was sharing my screen. Yeah, sorry. Okay.
Okay. So
okay.
Now you are seeing my screen?
Yes.
Okay, great. Okay, so I was doing the moving block model on the same data we acquired together. And you can see that here I don't have all the understanding of the process that I had before, but I can easily follow a line. What this line is telling me, how much my spectra are varying. So what is the difference between the standard deviation of a group of spectra at the beginning and the standard deviation of another group of spectra after a while, and then another standard deviation. So the standard deviation is a parameter that just summarizes differences. It's like looking not at the entire profile, but just at the modification. So what I can say is that if the moving block profile is going down, 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 it means that my samples are every time similar. So it means that here I have a high value of standard deviation. It means that the first spectra are really, really different, while at the end I have more similar spectra. So it means that the system is not yet changing. So this is the concept behind moving block.
And you can use the moving block standard deviation, so the standard deviation of the spectra, or over the time, or the area variation, so the moving block mean, okay, that is called MBM, okay, and also the RSD percentage, that is the ratio between the moving block standard deviation normalized divided by the moving block mean. Normally the moving block standard deviation as it is good enough. In a lot of cases has to be somehow confirmed looking at the moving block mean.
Yes, we decided to present it during blending because it's the blending is a more fixed system in which we know the ingredient that are putting inside. So the understanding that PCA is giving us, it's not so useful or request in blending, while in drying can be useful to understand what is happening inside our fluid bed dryer.
I have another good question. Thank you, Cristina. When we do a moving block method, let's call it like this, is necessary to have a wet chemistry analysis?
No, at all. So moving block method, like principal component analysis, are two approaches that are called unsupervised. It means that I'm just using the spectra. I don't need any work from the lab or any information about the sample, because I'm just looking at the variability, at the variation between one spectrum and the other. When I need the lab, when I need the wet chemistry, when I want to teach to the device, so to the MicroNIR, to give me a number, a percentage, gram per liter, or a class, if I want an answer that is not just something is changing, I need the lab. But for following a process, I just need to see the profile a long time. I just want to see how the process is varying a long time.
Okay, thank you. Another question that I can take it is when the temperature of the process is changing, what's going on to the NIR? Let me say that it's a twofold answer. First of all, we can keep pretty well under control the sensor. Every sensor has a temperature-based normalization, it's called a TBN function, that is compensating the variation of the temperature at the detector, let's say at the electronic level, and we can hold it dark before every spectrum in order to further compensate the temperature variation. Obviously, the temperature of the sample is something that we need to take how it is, so as to be modeled inside, because we cannot keep under control the temperature of the sample. We can keep our side under control, not the sample under control. But this is a classical stuff that happens in all the high shear or in the fluid bed dryer.